Yes, we are seeing it in
okay,
presentation
you see the
mode.
presentation, right?
Yes. Thank you. Floor
Okay.
is yours.
Good afternoon, everyone. My name is Andreas Margetis, and I'm working in the Parallel CFD and Optimization Unit of the National Technical University of Athens. I will present you here the methods that we developed in the framework of the exaFOAM project to reduce the computational cost and the storage requirements of the Unsteady Adjoint method in aerodynamic shape optimization. You might be familiar with the Adjoint optimization library, which was developed and made publicly available by our group in collaboration with OpenCFD, starting from the version 1906 and updated hereafter. The methods that you are going to see in this presentation are implemented as an extension to the Adjoint optimization library and focus on the efficient implementation of the Unsteady Adjoint method in aerodynamic shape optimization. Our target is to reduce both the computational cost and the memory requirements of the Unsteady Adjoint method using lossy and lossless compression techniques. Although the developed techniques that you will see here today are demonstrated using continuous adjoint in incompressible cases, the methods can equally well be used with both compressible and incompressible flows using either the continuous or the discrete adjoint formulation. Practically, anyone working with unsteady, multidimensional adjoint-based optimization problems may profit by the presented techniques. The main steps of an optimization loop are the following. First, we need to define the design variables of our problem. Although there are plenty of ways to do so, all applications this lecture is dealing with are based on free-form deformation. In particular, volumetric B-spline lattices, such as the one you see here, are used to simultaneously control the shape to be optimized and the surrounding CFD grid. In this case, the design variables are associated with the coordinates of the control points. Then we solve the flow equations to compute the flow solution, the flow field, the time series V, and the objective function J, and then we solve the adjoint equations to compute the adjoint variables psi. Having access to both the flow and the adjoint fields, the gradient of the objective function can be computed, our sensitivity derivatives, and based on them, the design variables are updated, and so does the surrounding mesh. All these steps are performed by the Adjoint optimization foam executable without requiring any third-party software or external scripts of any kind. In this presentation, we are focusing on the efficient implementation of the Unsteady Adjoint method. The distinguishing features of the Adjoint optimization library is that it is based on the continuous adjoint method. It includes the adjoint to the most widely used turbulence models, such as the Spalatal-Maras and the K-omega SST, and it also includes the adjoint to the grid displacement equation. All these features ensure the computation of exact sensitivity derivatives at a cost that is practically independent of the number of the design variables. If you want to learn more about the adjoint method and its implementation within the adjoint optimization library, you may refer to this article that you see here. My intention is not to focus on tedious mathematical equations. Allow me, however, to show you the governing flow equations on the left and their adjoint counterparts on the right. I've chosen the simplest subset of equations, assuming that the flow is laminar, to avoid unnecessary complexity. P stands for the pressure, V for the velocity, and τ is the stress tensor. Whereas on the right, you can see the notation that we are using for the corresponding adjoint variables. The most important thing to note here is that the unsteady adjoint equations are integrated backwards in time, starting from the last time step of the flow solver, and at each time step, the corresponding flow fields, the flow fields of the same time step, must be available. This fact significantly increases the memory requirements, especially in large-scale applications, and this is the problem we are trying to tackle. To give you an idea of the issue we are trying to face, let me give you some numbers regarding the computational cost that you see on the vertical axis and the memory requirements on the horizontal axis of the available treatments of this matter. For this purpose, let us use the well-known CHR car model provided to us by Toyota Motor Europe, which consists of 75 million cells and is run for 28,000 time steps. This case is also one of the industrial benchmark cases of exaFOAM. The first extreme treatment is the full storage of the flow field time series, so as this to be available during the adjoint solution. This approach has the minimum computational cost, since it doesn't require any recomputations of the flow, but the maximum memory requirements, which in this case reach 120 terabytes. That's with an amount that is excessive even for modern clusters. On the other end, we have the zero storage policy, combined with repetitive flow recomputation starting always from the initial state, which, as you may understand, comes up with a very high computational cost. A viable alternative most people are using is the binomial checkpointing technique, which reduces the memory requirements at the expense of a controllable computational overhead. Practically, what checkpointing does is to trade memory with CPU cost. To do so, the flow solution is stored at a number of checkpoints that are optimally placed along the time span to minimize the flow recomputations. It's a common practice to select the number of checkpoints so as to exploit all the available memory that we have. But even if we do so, the increase in the computational cost is not negligible at all. You see here that in this case, the cost increases by 45% from 37,000 CPU hours that the full storage strategy would require to 53,000 CPU hours per optimization cycle for binomial checkpointing. In exaFOAM, the purpose was to propose something better than binomial checkpointing, both in terms of memory requirements and computational cost. To this end, we developed the compressed full storage strategy, or CFS, which is based on a very effective compression kernel, the IPGDZ+ algorithm. As you see on the diagram, CFS clearly outperforms binomial checkpointing, both in terms of memory requirements and computational cost, as it reduces the cost per optimization cycle from 53,000 CPU hours to 39 CPU hours, while at the same time it requires only 350 gigabytes of memory. Let us discuss as briefly as possible what IPGDZ+ is. IPGDZ+ is a synthetic, lossy compression kernel which consists of three parts: the incremental version of the proper generalized decomposition, or IPGD, ZFP, and zlib. There is no need to go into detail for each of its constituent methods in this presentation. You may find more information about them in one of our recent papers that I've included here, if you wish. The main idea of IPGDZ+ is that it compresses flow fields incrementally on the fly each time a new time instant of the flow is computed without decompressing the already compressed time instance of the flow. IPGDZ+ operates as follows. It first uses the IPGD algorithm to compress the flow solution at a number of time steps. After that, the computed modes are lossily compressed using ZFP. And finally, the resulting ZFP streams are further losslessly recompressed using zlib. The extra feature of CFS, of the compressed full storage strategy, is that it offers the possibility to partition the time domain into consecutive and non-overlapping time windows, each of which compressed independently from the rest. And this approach offers certain advantages, reducing significantly the computational overhead of the compression and decompression. Overall, the compression parameters that the user needs to define are the number of IPGD modes, the number of time steps per time window, and a few parameters required by ZFP and zlib, such as the number of bits regulating the accuracy of the compression performed by ZFP. Let us now see some applications to quantify the benefits of the CFS strategy. Since CFS is a lossy compression technique, we will first examine the accuracy of the flow fields after their compression and decompression by CFS, and the effect the compression error may have on the computed sensitivity derivatives. After we make sure that using CFS is harmless in terms of accuracy, we will proceed in the evaluation of CFS in terms of memory requirements and CPU cost. We will first see the results of a series of URANS cases before we move on to some DDS applications. In all cases, our target is to minimize the time average drag coefficient, and all shapes to be optimized are parameterized using volumetric B-spline lattices. The first case is a motorbike, whereas the rest are car models. The driver, the ID3 model of Volkswagen, and the CHR model of Toyota, either in its half or full car configuration. The last case is, as I said also before, is one of the industrial benchmark cases of exaFOAM, and you can find everything you need to run this case in this reference. Each case has a different number of cells ranging from 1 to 75 million, use a different number of time steps ranging from 10 to 40,000, and it also uses a different number of CPU cores. In all cases, the flow is governed by the URANS equations coupled with the Spalatal-Maras turbulence model. In the two figures on the left, you can see the time evolution of the drag coefficient in the two CHR cases plotted with red color. In the same diagrams, the time average CD, computed as the simulation evolves, is plotted with blue color, and you can see that the time duration that we selected to solve the flow equations is sufficient so that the mean value of the drag coefficient has sufficiently converged by the end of the simulation. On the right, the time history of CD is plotted using either the exact fields, which are computed directly by the flow solver, or the reconstructed ones after their compression and decompression by CFS. It is very encouraging to see that the two lines practically coincide, demonstrating the high quality of the compression. In the same sense, the velocity magnitude around 3 of the vehicles is plotted. These plots correspond to the planes that you see in the right figures for each case, respectively. In the middle figures, the relative error of the velocity field is plotted after its reconstruction by CFS. You can see that in most of the areas the error is practically zero, with the exception of the wake of the cars and the area close to their underbody, where the error though remains below 5%. As a result, the impact of the compression on the computed sensitivity derivatives, which is the thing that we care most, since the sensitivity derivatives drive the optimization, is practically negligible and is below 0.5% in all cases. Since CFS is lossy, apart from the accuracy in the sensitivity derivatives, we want to make sure that the error that is introduced in the flow solution doesn't affect the course of the optimization either. As you can see for yourself, the evolution of the objective function throughout the optimization is practically unaffected by the lossy compression, irrespective if we are using the reference method without compression. Here the reference method is the binomial checkpointing technique, or the CFS strategy. In all cases, the objective function reduced 6 to 9%. And if you are interested in the optimization results themselves, the optimized shapes are shown in the port side of the vehicles as compared to the starting shape in the starboard side. Let us now examine the gains of CFS in terms of CPU cost and memory requirements. In all cases, the binomial checkpointing technique is used as the reference run, with the number inside the parentheses corresponding to the number of the checkpoints, that is selected based on the available system memory, which is different for each case. Instead of spending time in this table, which is actually given here in the sake of completeness, let's examine the summary results, which are more or less common for all cases. By using CFS, we managed to reduce the memory requirements compared to binomial checkpointing by 6 to 35 times, or compared to full storage without compression by 350 to 1200 times, so 2 to 3 orders of magnitude. At the same time, the computational cost was reduced by 30% compared to the reference run, compared to the binomial checkpointing, thanks to eliminating flow recomputations. In absolute numbers, if we examine the last case, the CHR in the full car configuration, that was the most expensive, CFS reduced the memory requirements by 350 times, from 120 terabytes to just 350 gigabytes. While it also reduced the cost by 15,000 CPU hours per optimization cycle, or in terms of wall clock time by 16 hours per cycle, from 56 hours to 40 hours. Somebody may wonder at this point why we don't combine the lossy compression techniques with checkpointing. Over and above to the work that we did in exaFOAM, we will present you here a new technique, which is referred to as the compressed coarse-grained checkpointing technique, or 3CP, which does exactly that. It combines checkpointing with IPGDZ+. The two techniques that we have now in our hands, CFS and 3CP, are complementary to each other, since with CFS, our target is to minimize the computational cost by eliminating the need of lower computations, whereas with 3CP, our target is to reduce the storage requirements as much as possible, allowing an increase in the CPU cost compared to CFS. In the CHR case, 3CP reduced the memory requirements by almost 2,000 times, from 120 terabytes to just 66 gigabytes, while it also managed to reduce the cost slightly by 2,000 CPU hours, or 4% compared to the reference run. If we examine these results in the graph on the left, we can see that the two techniques, CFS and 3CP, dominate binomial checkpointing in the Pareto sense, since both techniques outperform the checkpointing, both in terms of memory and cost. So far, we have used the URANS flow model. Nevertheless, as you know, the accuracy of URANS is not always sufficient for automotive applications. That's why we will evaluate CFS with the more challenging DDS flow model. Such higher fidelity models are much more demanding for the compression techniques due to the highly fluctuating nature of the flow, the finer resolved spatial scales compared to URANS, and the intense temporal gradients that appear in the domain. Here we will examine three cases. The first case is a concept car provided to us by Toyota in the context of a previous collaboration, which consists of 29 million cells and is run for 15,000 time steps. The next two cases are the CHR model, either in the half or full car configuration that you already saw in the URANS applications. In all cases, we are using the DDS version of the Spalatal-Maras turbulence model. The highly unsteady nature of the flow can be observed in rows 1 and 3, where the velocity magnitude is plotted on the symmetry plane of the two vehicles. In rows 2 and 4, the relative error of the velocity magnitude of the velocity field is plotted after its reconstruction by CFS. Despite the error being slightly higher in the wake of the car, but in any case it doesn't exceed the 5%, the accuracy of the sensitivity derivatives was almost perfect, since the error in them was below 0.5% in both cases. The results regarding the computational cost are pretty similar to what we saw in the URANS applications, since in both cases, you see here the results of the cases. I've excluded the case 4A, since the results are practically the same. CFS managed to reduce the cost around 30 to 35% compared to the binomial checkpointing technique, while at the same time the memory requirements were reduced 70 to 120 times compared to full storage. These two values, the compression ratios that we achieve, are slightly lower compared to what we achieved in the Urance applications, but this decrease in the memory savings that CFS can achieve is absolutely expected due to the higher complexity of the flow fields that need to be compressed. Nevertheless, CFS remains absolutely capable in storing the whole time history of the flow in lossy compressed form, all 23,000 time steps, eliminating the need of flow recomputations and reducing the cost by 35% from 64,000 CPU hours to 42,000 CPU hours per optimization cycle. This translates in a reduction of 1 whole day per optimization cycle in terms of wall clock time, from 67 hours to 43 hours. On the other hand, 3CP, the technique that combines IPGDZ+ with checkpointing, it reduces the memory footprint even further by 900 times, requiring just 110 gigabytes to compute to run the Unsteady Adjoint. At the same time, the computational cost reduces by 3,000 CPU hours or 4% compared to the reference run. To sum up, the compression of the primal solution time series was shown that it is extremely beneficial, both in terms of memory requirements and computational cost in Unsteady Adjoint optimization. The compressed full storage strategy that we developed is based on the IPGDZ+ compression kernel, and it was shown that it clearly outperforms the current state of the art, the binomial checkpointing technique, both in terms of memory and CPU cost. As a matter of fact, I've included the two graphs in the bottom where you can see the result of all cases that we examined. The 5 Urance cases on the left and the 3 DDS cases on the right, where it is clear that the message is common for all cases, that the CFS reduces the cost around 30% compared to checkpointing. If we examine the results of the last case, the CHR model that using the DDS equations, CFS reduced the cost per cycle from 64,000 to 42,000 CPU hours, or in terms of wall clock time from 67 hours to 43 hours. Assuming that we would perform 10 optimization cycles in the AWS cluster, the total cost of the optimization would reduce from approximately 30,000 euros to less than 20,000. This reduction in cost came without affecting the accuracy of the computed sensitivity derivatives or the evolution of the objective function throughout the optimization. Although CFS was demonstrated in this presentation with incompressible flows, it can equally well be applied with minor adjustments in compressible flows using either the continuous or the discrete adjoint formulation. Practically, as I said also in my introduction, any multidimensional adjoint-based optimization problem can profit by CFS. Note that CFS will become publicly available as part of the Adjoint optimization library of OpenFOAM upon the end of the exaFOAM project. Before closing, let me acknowledge BMW for funding the development of the IPGD algorithm, the exaFOAM project for funding the development and application of IPGDZ+ and CFS in industrial cases, and the special account for research funding of NTUA for supporting the development of the 3CP technique through a PhD grant. Computational time was granted by the National Infrastructure for Research and Technology. I've included in this last slide 3 of our recent publications, each one discussing different part of the algorithm, either the IPGD or the CFS and the IPGDZ+, in case you want to learn more about these methods. Thank you very much for your attention, and I look forward to answer any questions you may have.
Thank you a lot,